Record on.
Okay, hi everyone. So, good morning, so good evening, wherever you are. So, this in this session we are going to discuss about the graphs. So, last session we covered so many, tree problems around 12 problems on trees. So, in this session we will cover what are the different types of graphs and just the basic concepts of graph, and then we will also discuss one of the problems. Okay, so. So these are the simple definitions and the graphs. Like graph is simply a collection of nodes with edges between them, or some of them. So it's just a collection of nodes. You can think of graph as a just collection of nodes. Sometimes they are connected. Some of the nodes may be connected. Some of the nodes may not be connected. So it has nodes just like our trees. We also called vertex or vertices and edges. So the nodes, the connection between any nodes called edges. Okay. So Karan, so what do you understand about the graphs and directed or undirected graphs? What is the differences? You already studied something today, right?
Yeah.
Go ahead and
Uh,
you understand.
Graph, as you said, graph is a collection of nodes and edges,
Yeah,
uh, and each node have the neighbor node in a directed graph,
yeah,
which is a node the is pointed to the neighbor node.
yeah,
So, and graph is something we can say from a source to destination, from A to B, in the sense from a source to destination, which is a directed.
yeah.
If it is undirected, if it's no arrows are given, it is bidirectional. We can go from A to B or from B to A.
Exactly, exactly. Yeah.
So these graphs, directed and undirected graph, are represented by using adjacency list,
Mm-hmm.
where uh, each node in the graph is in the list, and each neighbor nodes are actually adjacency list is simply a hash map where each node in the graph A, B, C, D will be there in the list as a value, and
Yes.
their and their adjacent nodes are there are will be in an array for that value. So
Yeah.
each node will have more than one adjacent nodes, the neighbor nodes.
Each
So
node has more than one. So there could be more, like connections, maybe more, right? You are saying like, so this can connect to this can connect to this, right?
Suresh,
Can you see?
are you sharing your screen? Like,
Yeah, I can.
can
I'm sharing my screen. Can you see my screen
no,
now?
no, no, no.
Let me unshare and share again. Alright. Interesting. Welcome session. I'm sharing already. So stop sharing and share again. Yeah. So okay, share system audio and okay. How about now?
Where's this water bottle? Java.
Can you
Water,
can you see now?
water,
Yeah,
water, water,
Yeah.
water. Come on, come out, come out.
Are you okay? Someone came.
yeah. It's good. It's good.
So the graph is something like this, right? So from one node, there could be multiple connections, right? It can go here
Yeah.
and here, and there could be none as well. See, this node is just ideal. Let's say we have this node, so this is all itself is a complete a graph. This all the nodes can form as a graph, right? So so how many nodes in this graph?
6.
No, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Total 9.
How come? Okay, okay. This is also a node. Okay, okay, okay. Nine, 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 nine.
Everything is nine. Everything is nodes. So this is a complete graph. So basically, there is no connection between this node and the other nodes. This is a single node.
Okay.
Then this is, so that's why I'm saying like these are, you know, graph means the some of the nodes may not be connected, right? If it is a tree, every node somehow every node will be connected from the root, right?
Yeah.
So that is the
Okay.
difference. That is the difference between the graphs and trees. So you can, if you look at the sky and the list like a lot of stars, right? You can think of as a graph because they may
Okay.
not be connected, but that's a different stars, that forms as a graph. So here, so different nodes can be, some of the nodes can be connected, some of the nodes may not be connected, but this forms as a graph. So that is the reason you will maintain as a list. If there is a connection, right? If the connection is there, you can have the left node, right node, something like this, or adjacency list. So let's
Yeah.
say, yeah, let's say this is node A, and this is node B, and this is C, D, E, F, G, H, I. So so A is a node, and what is the adjacency list of A? So that means what are the neighbor nodes of A which are connected?
B, D, and C.
Yeah, so these three, right? But now, like, if you can maintain like this, every node contains, like, node contains the structure of node is data. First one is data, it could be character or an integer. Let's say the data contains A, right? And
Yeah.
adjacency list. Adjacency list, you can maintain all the neighboring nodes,
Neighbor
right?
list. Yeah.
It's a list of node B, C, D. So if you are maintaining like this, right? So um, so G, right? G
Yeah.
contains, G, the node for G is data. Data contains G here, and adjacency node, the adjacency list is null, but there is
Empty.
no connection. There is no connection to here, right? So where we need to start? How can we start? So basically, so this is a list of nodes. Even these two, H and I, right? So they have their own nodes. So in order to navigate, or in order to do the some process, right? So it's not like you start with A, you start with B or anything. It's like there could be 9 nodes, or there could be 100 nodes, which may or may not be connected, right?
Okay.
So how can we maintain this? So that's why the graph is a collection of nodes. So we will maintain the collection of all these nodes, right? So
Okay.
there will be node called H here, and there will be another node object called I, and H adjacency node has I, and I adjacency list has H. But now, how can we have all these different components in a single data structure? Because we need process. Let's say you want to count number of nodes, right? If you go with this, if you start with A, and if you start counting the adjacency nodes, you never be able to reach G, and you never be able to reach I, H or I, because none of the nodes contains H or I, right? There is no connection. If you start from A, you never be able to reach G, and you never be able to reach H or I, correct? If you start like a tree, and if you are going like all the nodes or next level and items, right? So you never be able to reach G because there is no connection,
Yeah.
right? So that's why you don't start with a node. So basically the graph, um, so the graph contains all these nodes. Basically the graph is a list of nodes. So this graph contains all the list of nodes. So that's why it's like it is defined as that. So here graph is simply collection of nodes with edges between some of them, right? Edges. So that's the main difference between the trees and the graphs. And what you said about directed graph and undirected graph is correct. So directed graph always has connections, right? So,
Yeah.
so here this is a undirected graph, correct?
Yeah.
A to B, B to C. This is similarly like directed graph has its own different format, right? So there will be connections between them. You can see an example. So it's quite easy to understand. See, this is an example of directed graphs.
Yes.
So yeah, so only like let's say if you look at this particular example here, so very slowly loading. Yeah. So if you look at this one, right? So we have connections between them, A to B and B to C. So you can navigate from C to B, but through like this, to C to A and A to B. So that's the connection, right?
Okay.
So how to represent the connection? So as you said, it's essentially through the best stuff. So, and if it is undirected, there is undirected means you can think of as a bidirectional, right? You can
Yes.
navigate from
A
any
to
node
B
to
and
any
B
node.
to A.
Yeah, A to B and B. So A adjacency list has B and B adjacency list has A. So you can think of this
Yeah.
like this. Yeah. So and graph may contain multiple subgraphs. So what is a subgraph? So
Um,
here, yeah, go ahead.
yeah.
Say
No,
something which
Suresh,
you
I
did.
don't have any idea of it.
So yeah, just a subgraph means a subset of the nodes. So here, right?
Okay.
So here you can think of this graph as three subgraphs. So this is one subgraph, right? And this is one subgraph, and this is another set components. You can think of as a component, right? So three
Yeah.
subgraphs. So that's basically subgraphs, and a connected graph is a graph that is connected in the sense of topological space. There is a path from any point to any point in the graph. So connected graph. So what is connected graph is like connected graph is little deviation from this directed graph. So connected graph means from any point to any point you can directly go to any point to any point. Let's say the directed graph here, right?
Okay.
So what is the difference between? Let me explain you this. So you saw this diagram here, right? Can you
Yeah.
go from C to B?
Uh,
Still open. Just a minute, it's still opening. So here, right? Just open here. Yes. Yeah. Let me open this. Okay. So now, can you go from C to B? Oh my God! I'm clicking and it's opening something. Wait a minute. Okay. Finally. So can you go from C to B?
C to B is possible only through A.
Yeah.
No
Right.
direct.
So only no direct connection. Can you go from D to B?
D to B. No. There is
Not
no
possible.
outgoing. Yeah. For the,
There is no connection, right? This is a directed graph, but there is no connection. But connected graph means every node is connected to every other node. So
okay.
something like this, a series on a connected graph is a graph that is connected in a sense of topological space. There is a path from any point to any other point in the graph. So
Okay.
let me give you, I think there are some examples here. So like this, it's still opening here. If you can see on the right side, see from any point to any point, you can go from any point to any point without. Yeah, here is an example. Connected graph, connected graph. You can think this. This is an example of connected graph. Yeah, k vertex connected graph. So it is from this point you can reach any point, right?
Yeah.
See,
Every other
similarly for
node is
any
connected
point.
with each other.
Exactly. Every node, every pair of nodes, there is a connection. So that's the connected graph. So here are the other connected graph examples. But anyway, so that's the representation of the connected graph. And Have you know? Did you know about like the cyclic and acyclic graphs?
Cyclic graph forms a cycle inside the graph where we
Cycle
can
inside the graph.
uh,
Yeah.
we can have a particular cycle again and again inside the graph if we go through a path that won't be
Yeah.
ending.
Acyclic. Acyclic means there is no cycle in the graph.
Graph, yeah.
Yeah. So it's like cycle means it will no ending, right? You can keep on cycling. Like if you start with the nodes, it will keep on going. So here is different connected graphs. Look at this. I don't think this first one is connected graph, right? This is not connected graph.
No.
Figure 5 available, create common attributes. Yeah, this one is not connected graph either. They are giving some examples, but anyway. So cyclic graph is cycling. Like if you have cycles in the graph, probably cyclic graph only for the directed graphs.
Yeah.
Because if you go with this without the cyclic graphs, they define here a graph contains at least one graph cycle. A graph that is not cyclic is acyclic. A graph is passing exactly one unidirection simple. The cycle is called unicycle graph. A cyclic graph that are not tree. Cyclic graphs are not trees. So basically, it's loading really slow. So maybe we should draw our own. So let's say we have something like this, right?
So Suresh, for our programming input, they will give the adjacency list, right? Not the graph.
Uh,
List will be
I will
taken
tell
as
you.
input.
Yeah, I will tell you. Yeah, so there are two things they will give. In the graph will be formed as a list of nodes. They will give list of nodes
Okay.
because if you give existency, let's say if you give existency list, right? So how can you navigate to these nodes? Let's say we have these separate nodes. So none of the adjacency list of any of the nodes does not contain these nodes, right?
Yeah.
Because there is no connection. So that is why adjacency nodes is not the correct input. So I will tell you that. I will come to that. So let's figure out the definitions, and then we'll come to the representation, how to represent. Okay. So here is a cyclic graph. So did you find a circle here? There is a cycle here, right?
Yeah.
So here is A, here is B, C, D, E, and C from B to C, C to D, and D again going back to here.
To
So
B.
there is a cycle here. So if you see something like this without cycle, let's say we have E, so A, B, C, D, E. So there is no cycle here,
Yeah, there is no
right?
cycle.
So there is no cycle. So, but you can think of actually the tree is also a graph. If you look at the tree is a cyclic graph, correct? Because there is no cycles in the tree, right?
Yeah.
Tree is a connected graph without cycles. So there is no elements like this orphan elements. Tree contains always all the nodes are connected, right? All the nodes are connected, and there is no cycles, something like this. There won't be something like this, right?
Okay.
So tree is a connected graph without any cycles. Do you agree?
Okay.
Tree is
Yeah.
also a graph. So if you look at this one, this is exactly a tree. So if you look at this tree here, this represents a tree here, right? So a right node, let's say you can think of as a right node. A right node is B's right node is C, and C's left node is D, and D's right node is E. You can think of this as a tree, correct?
Yeah.
So tree is also a graph. but every node is connected. That is the only difference. So every node is connected. There is no node something like this, which is not connected to any of the other nodes. But graph contains node like this. Graph contains an orphan nodes which doesn't have any connections to other nodes. Okay, and there is no cycles in the tree. If there is a cycle in the tree, if there is a cycle, that never be a tree, right?
Yeah.
So that's why they are treating as like tree is a connected graph without any cycles. And we already discussed about this adjacency list. What is adjacency list? Is basically
The
the
list of nodes.
vertex. Yeah, the list of nodes that each node is connected. Let's say what is the adjacency. Let's say we have something like this, right? So adjacency list for this node is 1, 2, 3, 4. All these four are adjacency for this one.
Yeah.
This node has two adjacency nodes, this one and this one. So these are the two adjacency lists. So we can go to
Okay.
the representation, how to represent, and we can also look at the first problem here. Find connected components in a graph. This is one of the interview question. What are the connected components? So if you look at this graph, let's go to the first graph here. I'm representing here. Connected components means the ones which are connected, right?
Yeah.
So let's say something like this. So this is the whole graph. How many nodes in this graph? One, two, three, four,
2,
five,
11
11. Exactly. So we have 11 nodes, and how many connected components?
connected component.
Basically
Two.
subgraphs. You can think of as a subgraphs.
Three subgraphs are there.
Exactly. Three subgraphs. This is one subgraph, and this is second one. This is the third one, right? So this is a subgraph which is all connected, and here is one more subgraph, and here is the third one. So we need to return 3. So we will get all the 11 nodes in a graph, and we need to return number 3 as a result. So how can we do this, right? So what is the representation? How to represent? Now you are asking about representing, right? So we can come to that. So I will show you. So as I said before, every node contains a node structure, right? So here is the
Yeah.
thing. So let's look at this example here. So A, B, C, D, E, F, G, H, I, right?
Yes.
So this is like a connected. This is another connected component, and this is also connected component. So we have 3 connected components, right? So how many connected components in a graph? Given graph. This is a single graph with 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes, right?
Yes.
This is a graph with 9 nodes, and there are 3 connected components. So how to represent this? This is a representation. So can you see here? So simple like node class. This is structure of the graph node. This is not the graph. This is the structure of the each node in the graph, right? So first one we always know data. It could be character. It could be integer, or it could be employee, right? Let's say every node is employee object. Okay, that could be an employee here. So this is the actual data, and here is the next node is basically the adjacency list. This is a list of nodes, right?
Yeah.
It's not like left or right, because there is no left or right in graphs, right? It's just all what are the neighboring nodes, right?
Okay.
It's just a list of nodes. Okay, so here is just a public constructor where you can define the data. You can create a constructor. You know that, right? And here is the get adjacency list, just a method which will give you all the adjacency nodes, and character data. If you want to get the data, it will give you the data. So that's it. That's it. Here only two things: data and adjacency nodes. For any node, this is the only thing. So now but we need something which will contain all the 11 nodes, right? Because
Yeah.
start with A, you never be able to reach these nodes. That's why we need to graph. We need to maintain the graph. This is the representation of graph. Graph is nothing but a list of nodes, right? So that's what the definition we had in the beginning. The graph is simply a collection of nodes. That's it, right? So
Mm.
simply the graph will contain public list of nodes.
Okay.
So how many nodes in the graph? In the given graph, let's say here, how many nodes we have? One, two, three, four, five, six, seven, eight, nine, right?
Okay. Yeah.
So nine elements in this graph. So the graph contains all the nine elements. Okay. So but each node in the graph can have their neighboring nodes. Let's say you can think of as a population. Let's say your city has like nine. Let's say you class. Let's say you have a small class of people, and there are how many students in the class? There are nine students in the class, right? Now these three are connected. That means these three ABC are friends, and DE are separate friend circle. FGHI are separate friend circle, right?
Mm.
But
Mm.
from the graph perspective, you don't care. From the graph, from the teacher, let's say how many elements you are representing the class. Let's say you are the teacher and you're representing the class, or you are representing the entire class. How many name element? You simply have all those in your pocket. Nine. When you're taking attendance or something, you will go with all the nine, right? You don't maintain some of the elements. You will maintain all the items, all the people in a single list. Okay.
Okay.
But connections wise, they have their own connections. Let's say these are the only ABC are friends. So if you ask A, hey, who are your friends? A will say only B and C. B and C are my friends because they are neighboring nodes. They are connected. If you ask about D, D says only E is my friend because that's connected, right? That's how it is. The connections will be represented in the adjacency nodes. So
Yes.
now if you look at the representation, you can see here. So we just define a graph. Okay. G dot nodes equal to, we are defining, we are creating the object of the nodes, and now I'm adding all the nodes A, B, C, D, E, F, G, H, I, and so all these nodes I created. Now look at this. A dot next nodes dot add B.
Okay.
Similarly, B dot next node dot add A. So basically, creating a directional, bidirectional. A next node contains B. B next node contains A. Next nodes is
Yes.
basically next nodes is basically the adjacency list, right?
Yes.
Similarly, A dot next node dot add C, because basically I am creating a connection from A to C, and again this is a connection from C to A.
Mm.
C's next nodes contains A. A's next node contains C.
Yes.
Similarly, B next node contains NC, and like C next node contains B, right? So
Okay.
just adding all the connections. So D contains E, E contains D, right?
Mm. Yes.
Similarly, F contains G, G contains F. So I'm like bidirectional, adding all the connections. Now you have all the connections. Now A contains, let's say if you take A node, A next node contains B and C, right? So similarly,
Yes.
if you take F, right, F contains G. So F contains G, and that's what here, right? F only connected with G, right?
Mm.
G connected with H. So that's what I represented here. G next node, G next node contains H. Of course, G also connected with F because it's a bidirectional, right? So if you look at
Yes.
from G, G connected with F and G connected with H.
Okay.
So that's why I added here G. G next node contains F, and G next node contains H. Okay.
Oh, yes.
So just adding those nodes. Now you added all the nodes. Now you have all nine nodes, and you also added all the connections. Now you want to add to the G. G is actually the graph, right? So if you look at here on the line number 55, we just created the graph, but we did not add any of the nodes.
Hmm.
So now we are adding all the nodes, simply all A, B, C, D, E, F, G, H, I, all the nodes into the graph G.
Graph.
Because here G doesn't contain any connections. G is just a node, just a list of nodes. If you are taking as a attendance list, you don't maintain the connections between those people in your attendance list, right? As a teacher,
Yes.
what you just maintain list of students. That's it. You don't care how many of those connected or not. You don't list in your register. If anybody asks, hey, how many students in your class? Okay, I will say simply nine because all these nine nodes.
Hmm.
But here the problem here is the algorithm is number of connected components. If I'm asking you, hey, how many friend circles in your class? Let's say we have nine people in this class, but these three people are connected. These two people are connected, always kind of friendship. They go for lunch, they go for play, and these four people always get together, right? So how many components? How many connected components?
Three.
Three, right? That is what we want to figure out. So if somebody asks you like, hey, we have these students, you have nine students, but tell me the connections. So how can you tell here? Because by looking at just here, by iterating from G, you cannot tell. G contains all nine, that's it. So we need to go to each node and find out connections, right?
Okay.
So did you have you practiced any other problem than this, or you just looked at the graphs?
I started with a traversal of a graph.
Traversal, yeah, this also contains traversal, because unless you traversal, you cannot find you cannot find the components, right? What kind of traversal you went with? The BFS,
Depth,
DFS?
yeah,
Yeah, okay,
depth
okay.
and breadth first.
Depth and breadth, yeah, this will also cover the same thing. So how did you traversal breadth first it? Yeah, explain whatever your findings. Where,
Breadth first.
yeah,
For I started with the first node actually.
but there is no first node here, right? The list of nodes, basically first node in the sense, basically maybe the first node in the graph, right?
Yeah, first node in the graph.
Yeah.
And I for breadth I have identified the neighbor nodes
Okay.
and pushed them into the queue, whereas before first in first out.
Exactly. Exactly. Yeah. Yeah.
So from the queue, uh, now I'm going to pop one, take out the first node. Actually,
Hmm.
the
Yeah.
first in first out. Yeah.
Yeah.
Take out the first node which is in the front,
Yeah.
and for that I'm going to identify the neighbor nodes
Yeah. But if you
and
look
then
at,
push
let's say you visited A and you put B and C in the queue,
in
right?
the yeah.
Now you take out the B and you are trying to find the neighboring nodes of B, but
Mm.
neighboring nodes of B contains again A and C.
Okay.
So then what you going to do? Are you going to put A again into the queue?
No, Suresh, I'm not going
Yeah.
to do that.
So how
So
yeah, what you did, like
this
the algorithm, yeah.
problems.
You
Yeah.
take out the first element from the queue and you look at the neighboring nodes. Yes.
Yes.
Go ahead. Yeah.
For B, for B it is C. For A it is B and C, and for B it is C.
Yeah.
D, so, okay. In that case, I can check whether the node is already popped
Yeah.
or taken in and
Yes.
quit that
Yes.
option.
Yes. So we don't want to go around and around, right? So because this is a bidirectional, right? So if you start from A, what are the neighboring nodes? B and C. Then if you start from B again, what are the neighboring nodes? A and C. So like you don't need to navigate if you already navigated. If
Okay.
it is tree, right? If it is tree only, you cannot go up. It always go down. So it's okay. You can simply get the nodes and put it in the put it in the queue. But here there is another complexity. The main complexity here is every adjacency, like every node contains its adjacency nodes, so you will find
Okay.
duplicates, right?
Oh, okay.
Are you following? So here, if you look
Yeah.
at right, A, right, A next node contains B, and B next node contains A.
Yes, yes,
So
yes.
that's why when you're asking like, hey, give me the adjacency nodes of A, you will get both B and C. And now again, if you're asking B, what are the adjacency nodes of B? Again, you will get A and C.
Okay. We have to check whether the node is already explored, right?
Exactly. That's why you need to use some kind of data structure that will tell you easily what is the data structure that will help you to identify very quickly whether you already visited A or not.
Mm.
You visited A, and then you started visiting B, and you want to visit the neighboring nodes, but neighboring nodes A already visited. So how can you identify?
Mm.
What is the data structure that will help you to with order of one, like visited or not, or like if you want to find out
Array?
array,
No.
you can put in the array, but let's say if you have 10 elements, you need to navigate whether A is there in the array or not, right? If you have 100 elements, you need to
Hash
navigate.
map?
Exactly. Hash map or hash table, that's very good data structure that will tell you with just order of one, right?
Yeah.
That's what we do. That's what exactly we do here. So yeah, so if you look at that algorithm, that they will definitely use the hash map or hash table. Okay.
Okay.
Same, yeah, hash map or hash table. So here is the graph. So let's look at that. So once you use the hash map, right? So you navigate from A and you navigate from B. And so when you navigate to the B, you looked at the adjacency nodes A and C. So A is already in the hash map. You no need to navigate. Now you navigate to the C, right?
Yeah.
And now you see adjacency nodes contains both A and B.
A and B. I
But
need
A
not
and
to
B already in
navigate
the
the
hash map. A and B already in the hash map,
hash
right?
map.
Now you look at any other adjacency list. Do we have any other nodes? No.
No.
C is not connected to any other nodes. Then we are done. So basically, you completed breadth first search or of from A to ABC. Now,
Okay.
but that doesn't give you the connected components here. You need to look at what are the other components. D and E there, F, G, H, I also there. So what you need to do, you need to go back to the graph and ask, hey, I processed A, B, C. Do you have any other nodes? Give me any other nodes. You need to ask the graph because graph contains everything, right?
Yeah.
Graph contains all the nodes. Even graph
Yes.
contains like D, graph contains E, graph contains all the nodes. But when you start with a node, you navigated only A, B, C. So what you need to do is you need to ask the graph again, give me the next node. Okay. So when you ask first time, it will give you A. When you ask second time, the graph will give you B. When you ask third time, it will give you C. But when you ask second time A and B, when you ask second time B, you already visited
Yes.
because graph don't know, right? Graph will give you each node. Graph will give you, hey, take A, and you process A. And if you're asking graph again, it will give you B. You said A, I already processed. A is already connected to B and B connected to C. And if you give C, I already processed. Now give me another node which is not processed, D. Then you start processing how many nodes
Okay.
from D connected. That's what the main
Okay.
purpose. That's basically when you start when you start some when you find something a node which is not in the hash table, then you increase the components, right? So let's say connected components, how to calculate here is, so hash table count equals 0. So you initialize get connected components. We created a method called get connected components. Okay. And we are taking
Okay.
G is input, graph is the input, And as you said, we took a hash table. Okay. Now count equal to 0. We initialize the count, number of connected components 0. Okay. Now, as I said, just iterate all the nodes from the graph for each, for each kind of node, for each kind of loop, right? What it does is it will give you each node from the graph, all the 9 nodes. You will get all the 9 nodes, right?
Okay.
Now we are checking whether this node contains in the hash table. If the node does not contain in the hash table, that means that is a very brand new node. Correct?
Yes.
It never processed. First time,
Okay.
like hash table, if you are taking a node, let's say you started with F. F is not visited. Like if so, F will not be in the hash table because even if you start with A or B or C or D, you never be connected to F. So
Discovered it. Yeah.
F is a brand new node you are visiting first time from the graph. That means this is a one different component, connected component. Basically, connected. This could be connected with another nodes, but this is an independent component, right?
Okay.
That's where we are incrementing the counter. So first time when you get A, right? When you get A is not part of the hash table, so we will get count equal to 1.
Okay.
Now we are immediately adding that A into the hash table. Hash table or hash map, actually there is no second element required, so we can use hash map where we no need to add any value, so just a key is enough. So now process all nodes reachable from this node. That is the next step we do. You just started with A first time, right? When you start with first time algorithm, you started with A. Now process all the nodes reachable from A. Okay.
Okay.
What are we doing? Processing is actually the breadth first search. As you said, process all the nodes from this node, and we are also carrying the hash table because
Okay.
we need to carry hash table because we have to add the nodes that you are visiting into the hash table. We don't want to count, right? We don't want to count. We don't want to increment the count for B or C because they are reachable from A.
Mm.
Correct. So whenever the
Yes.
graph gives you B, we don't want to count it. Whenever the graph giving the C, we don't want to increment the count. That's why we are sending that hash table. Hey, take this hash table and put all the nodes that you can reach from this node into the hash table.
Okay.
That's what the process. This actually the same process what we explained. Processing. This is exactly like a normal BFS. Normal BFS, what we do, breadth first search. This is a node you need to start, and this is a hash table, and we also maintaining a queue. As you said, this is perfectly all right. So we are creating a queue, and we added the elements into the queue, and if the queue not equal to null, we are processing at q dot
Okay.
q q if q not equal to null. For each queue, this is the adjacency list, right? Get all its adjacency nodes. So
Okay.
when the node is A, right, it will give you all adjacency nodes of A, which is B and C,
Okay.
right? So here is the main trick here. We don't want to add a node which is already in the hash table. That's why we are carrying here, right? If this new node is not in the hash table, add to hash table
Okay.
and also add to the queue. We don't want to add unnecessary, right? So here is the trick. So let's say you are processing B. So you process A. Initially, you process A, and what are the adjacency nodes of A? You will get B and C, right? Maybe if I can draw here, that will be very easy.
Yeah.
So you have node A, and you have B, and you have C.
See.
And initially, of course, they're all bidirectional. So what we did here is we got hash table. Hash table contains A. A already added to the hash table, right? So here is the hash table. hash table contains A. Okay, hash table or hash map. Okay, now Q is empty. We took the Q as empty. Okay, so now of course these are all bidirectional. So now if I ask you the adjacency of A, we created a Q empty Q, and we dq. So now we added A into the Q. We added A into the Q, and immediately we dq'd that A. Now Q contains empty. Now we are processing A. What are the adjacency list of A? Right? We are asking, hey, give me all the adjacency nodes of A. Okay. A adjacency nodes contains B and C. Right? Does B is part of the hash table? No, B is not here. Right? Now what are we doing? We are putting B into the hash table. We are putting B into the hash table, and we are putting B into the queue.
Q, and
Now
we
we
are
are
DQ.
checking what is other adjacency node C. See, we are putting C into the hash table, and we are putting C into the queue.
Q.
Right? That's it. We processed A. We are done with A, and it will go back here. Now Q is empty. No, Q contains two elements. Okay. Now DQ the next element B. We DQ the B, and we do the same thing. Give me all adjacency nodes of B. What are the adjacency nodes of B? Adjacency nodes of B is A, C.
C.
A and C. Both A and C, because A is bidirectional, right? B connected to C, B connected to A. Now we will check the
Yes.
condition. Now we will check the condition. Hash table doesn't contain B. If the new node is not in the hash table, add to the hash table.
Okay.
Node A.
So then
A
C
is
will
already in
get
the
only
hash
added.
table. What's that?
C will get only added.
Wait, let's start with A. A already contains in the hash table. Don't do anything. Now C. C contains in the hash table. Yes. C already there.
Yes.
Because
Yeah.
when you processed A, right, you added B and you added C.
Yes.
So that's why both A and C already in the hash table. So don't do anything. So we no need to add to the hash table, or we no need to add to the queue, because it's already added,
Okay.
right? So nothing. And let's say if you have any node, something like this, if you have something like this, then that will be added to the hash table, and that will be added to the queue. But there is no node like that. There is no node which is going away from B. There is no other node, right?
Yes.
Let's say if you have a node, let's say if you have a D, then D, when you are processing D, there is no D is not there in the hash table. D is not there. Then we will add D here, and we will add D here. Or D, you can think of let's X. I don't want to call it, because D is already there in the other graph, right? So
Yes.
so let's say X. So X is, we are going to add X in the hash table, and we're going to add X in the queue. Now what we do is, we are done with B. Okay. Now we will go
Yes.
to the next node in the queue. Next node in the queue is C. What are the C's have adjacency nodes? We are going to process C. C adjacency nodes are A and B.
Hmm.
Now we'll check, is A in the hash table? Yes. Don't do anything. Is B in the hash table? Yes. Don't do anything. We are done, right? So B is done, C is done. Next one is X. We are
Hmm.
going to process X. Okay, take the X, and what are the adjacency nodes of X? Here is the X. Adjacency nodes of X is, what is the adjacency nodes of X?
X is B.
Exactly. Only B, right? Because B, it's not connected to any other node. So now we will check, is B already in the hash table? Yes. B is already in the hash
Yes.
table. Don't do anything. Now nothing in the queue.
D is
And
good.
now we are done with queue processing, right? So now what happens? This method will simply return here, go back to here, and we started with A, and we processed all these A, B, C, and X, right?
Yes.
Now what happens is, that is one component. So that is one connected component. Now this will
Okay.
go back here, Now next node comes from the G. What is the next node from graph?
Next node from graph is D.
No, first it gave you the A. The graph
Okay.
contains all 9 nodes. First time you got A.
Yes.
Second time you got,
Okay.
so first time
D.
the
Okay.
asking graph, you are asking graph, give me all the nodes from the graph. You, you,
Okay.
you, you got
Then it will
you
be
got
a B.
you got A. Now you get
B.
B. But do you want to process B?
No.
No, because you already processed B, right? A, you
Yeah.
started with A and you already processed B and C.
B.
That's the condition here. We are not going to process. We will check whether hash table contains that node. Does hash table
No.
contain that node? B is there, right?
Yes.
B is there. That's why don't do anything. It's already counted. It's not new component. It's already
Okay.
connected with A. So that's why we will have additional. So this is just a extra complexity, extra hash table on top of the breadth first search. Breadth first search is only this one. It doesn't contain hash table. If you look at the tree breadth first search contain, you never contains any hash table. But here we are maintaining an additional hash table in order to have this condition. We don't want to process B because it contains in the hash table. So hash table does not contain, then only process. So count is
Okay.
still one. Next node. What is the next node from graph?
C.
C. This is also in the hash table, right?
Yes.
So we just looked at A is there, B is there, and C is there. Now what is the next node? D.
Next node is D.
D. Is D in the hash table?
Mm, no, it is not in the hash table.
Is
So the
not in the hash
process.
table. Exactly. Then we will count. We will increment the count. So count until now is count is one because when you started with A, when you started with A, we count equal to one. Now count equal to two. You are starting with D, right?
Yes.
So now what we do is again we'll process. We start the process again, the same process. Okay, process. You added D into the hash table. You count, increment the count, incremented the count, and you add D into the hash table. Now you start the processing. Breadth first set, right? From the D you start the processing. You took a queue again. This is empty queue. Okay, now you took a queue and you are going to add D into the queue, and then your dq, you're going to dq. And what are the different adjacency nodes of D connected with E, right?
Yes.
So E is, no, we'll check the same thing. Is E in the hash table?
Uh,
No.
no.
Add the hash table into the, add the E into the hash table and add E into the queue. So it
Q.
processes the same way. So add E here and add E into the hash table and to the queue as well. Now process E. So E contains, we'll take the E,
D.
and E is already in the hash table, and E's adjacency is D. D is already in the hash table. Don't add anything to the queue, right?
Okay.
So that's how it is. So every node you start with every component, and you process a breadth first search,
Okay.
right? So
So now the
now when,
connection becomes two.
what is that?
Now the connections becomes two. The connected components becomes two. After
Exactly. Yeah,
complete.
we already incremented that. As soon as you
Okay.
start with a new node, as soon as you encountered a D is not like visited before. We are incrementing the count. So now what happens if you ask for the next node? It will give you after D. It will give you E, but
Yes.
E is already in the hash table, so you don't increment the count. Now when you ask for the F, is F in the hash table?
No, it is not there
No.
in the hash table.
That means you are encountering or you're exploring a new component which never be visited before. That's why you are incrementing. right?
Okay.
So now count becomes 3. Count becomes 3. That means total 3 components. And now from starting from f, you are putting f into the hash table. It does the same thing. You put the f into the hash table, and if you process f, right? If you process f, all other nodes g, h, I, everything will goes to the hash table.
Okay.
G, H, I, because all are connected, right?
Yes.
Right? So all are connected, and by the time you process F, everything is connected. Now, if you come back here and if you're asking for the next node will give you, we will get G, but G is already in the hash table. We don't increment the count. H is already in the hash table, and I is also in the hash table. We don't increment the count.
Okay.
Finally, the count will be 3.
Okay.
Is that clear? It's confusing, but
No, no, no,
um,
no. So it's clear. It's clear.
yeah. Only difference here is if you look at you can look at the side by side comparison as well if you want. But the only difference between the normal breadth first search and this is hash table is the only thing. So we can also look at that actually very
Shall we
simply.
achieve this to using depth for search?
We can do that's a good question. So if you go to depth first search, right? Um, yes, you can do with depth first search as well,
Okay.
because let's say but you have to maintain that hash table. Depth first search means you start with A and you go to
Yeah.
B and you go to C, right? You don't it will go recursively,
Okay.
right? Yeah, you can definitely do with depth first search, no issues.
Oh,
Yeah.
okay.
So only thing is it will use a stack rather than queue.
Mm.
So that's not a problem. Let's say if you have something like this, right? So you will visit A, B, C, X. So you visit A and then you visit B and then you visit X, right? It will go depth all the way to the depth of the tree and then go back. Okay. What are the other nodes of B? Then it will visit C, right? It's
Yes.
totally fine. It's totally fine. Anything is fine. Yeah.
Okay.
Yeah. So that's a mainly connected component algorithm. So if you want, we can look at the uh, what is that one? So we can. I want to just compare the algorithms, like basically the depth first search of the tree versus this one. So if I go back my projects and .NET Core, um, tree BFS tree. We have tree depth first search, right? This is depth first search. Yeah, here is the tree BFS. So I want to compare. If we can see side by side, right? Then
Okay.
we can easily see what is the difference between tree depth first search versus the this one,
Breadth first.
tree BFS. What? Why it's not working? Oh, maybe I should do different way. I should do new Visual Studio Code. File open. Open file. Open folder. Maybe open folder. Come on. Just a minute. This one go here. This one go here. My projects. .NET Core and tree BFS tree breadth first tree BFS. Yeah. Hold on. Yeah. Now let's look at here. The tree always starts like this. See, here is the tree, like 1, 2, 4, 2, 3, 4, 5, 6, something like that. It will go like that. And here is the breadth first search, breadth first traversal. Let's look at the traversal, not the search. So, okay, what we do here, we simply maintain a queue. We started with root.
Q.
We started with root,
Okay.
and we will simply maintain a queue. And the same thing, we added a root into the queue. We removed element from the queue, and then we'll print that. And we
Look
added
at
all the childs. We added all the childs into the queue. Only difference here is we did not check whether child is already
that.
visited or not.
Okay.
Only that is the only difference, because we maintaining another hash table to make sure that node is not visited before. Because in a
Okay.
tree, right, in the tree you always have after 1 2 3 4, right? So there is a possibility that you already visited before, but here there is no possibility like that, right? Because two connected to 3 connected to 4, and this kind of connection exists in the graph, right? See, A connected